All right, here we go. 6.4 arc length. You certainly can imagine this being an application in physics, certainly in bridge building, right? I've got a certain density of steel, how much arc, how much length of this cable would I need to support it, or, that, I guess I'm reaching a little bit there, but all of these integrals will be applications in our field, except for maybe some computer science. But you're going to be programming these applications for the rest of us. So our arc length formula, L, is the integral from A to B, and I'm assuming no loops here, no repeated pieces, of the square root of don't tell me. I forget it. Let me look it up.
I guess dx dt plus dy dt.
Yes. I want to just make sure because I want to write down the one of them first. Yes. Dx dt squared plus dy dt whole squared with respect to t. So you can see I'm doing parametrics here, and when I prove this, when I derive this formula, I'm going to derive it with parametric equations. And what do you see there? What do you see there? If I give you that formula, what do you notice?
It's like opposite squared plus adjacent squared.
Exactly.
Square root of that. So ax plus Pythagorean theorem. That's
exactly.
It.
So and if I just look at an arc, right, from A to B, and I did one section of it, I can estimate that arc with my right triangle, right? And so the length of the hypotenuse there is close to the length of the arc. Not good, right? It's not perfect. But then what do? Well, let's cut it in half. And so now let me do this right triangle and this right triangle. And now we'll look at the two arcs, the two hypotenusae, I think that's right, added up are even closer to the length of the arc. And I'm going to keep doing that, right? I'm going to keep splitting it into partitions and calculating the length of the hypotenusae and add them up, right? And then it's going to get me. So when I derive it, you'll see that's the process I'm going to do. So let's just do one quickly and see how we do, right? Let's do the arc, the circumference of a circle, right? So circumference of a circle will be our first. Right, so what do I get? X equals cos theta. So this is the radius is 1 here, right? And y equals sine theta. I'm gonna take or cos t, right? I'm using theta instead of t. I can use t. I'm sorry. It's the same thing, right? Theta starts with t anyway, right? So what do I get for dx dt here, right? What do I get for dx dt? The derivative of cosine is
minus sine x.
Yep, minus sine t, right?
Yeah. Sorry.
Yeah, it's okay. And then dy dt, that's the derivative of my sine, which is cosine, cos of t. right? And then what do I want to do with each of those derivatives? I want to square them, right? So dx dt quantity squared is going to be sine squared t, and dy dt quantity squared is cos squared t, right? So and where am I going here? What should be my a and b here? If I'm doing the arc of a circle, what should be my a and b? Where did my loop start? Where did it end? Right? 0 to 2 pi, right? So I have square root of sine squared t plus cos squared t dt. How are we doing here? Everybody following? I didn't derive the formula yet, so you're kind of trusting me a little bit, right? First time we taught you quadratic formula, we didn't show you where it came from yet. We did a couple problems first, and then we derived it and tortured you. So what do you notice here? Sine squared t plus cos squared t is 1, right? So this is now the integral from 0 to 2 pi of the square root of 1 dt, which of course is just t. And I'm going to evaluate at 2 pi and then 0, and then I get 2 pi. 2 pi r, right? Remember, my radius is 1. Pretty simple, right? This is number 7. Am I ready to do the next example? So very simple, very simple. It's nice to have something simple after 6.2 and 6.3, right? After seeing the hell of 6.2 and 6.3, it's nice to have something pretty simple to let the brain calm down a little bit. So this is 6.4, number 7. And I have find the length of the curve, right? So the length is from 0 to 1 of dx dt squared plus dy dt squared dt, where x is 1 plus 3t squared and y equals 4 plus 2t cubed. And most of these just turn into this hideous algebra, which you're used to from Calc 1, right? The algebra was a lot worse in Calc 1 than it is in Calc 2. We don't care so much. We know we already tortured you with the algebra in Calc 1. So I need derivatives here, right? So I know dx dt is 6t, right? And I know dy dt is 6t squared. Right? We agree with that? And I'm going to square both of those, right? So 6t squared is 36t squared, and 6t squared quantity squared is 36t to the 4th. All very easy so far. So it looks like our arc length from 0 to 1 is going to be square root of 36t squared plus 36t to the 4th dt. Don't let me go too fast here. Nice to see 100% attendance again. I know things happen. I know some days we don't feel good. Some days we have to take care of family. Some days we oversleep. You really want to make sure you don't miss the exam. So I'm kind of asking you, get a nice schedule for next week. Try and be ready for class early. On the day of the exam, I'm asking you to come in 15 minutes early, right? You know, you can set a couple of alarms. You can ask someone to give you a wake-up call. Whatever you need to do, right? So I can take out a 36t here I can factor, right? So I got a 36t squared. And then what do I have left over? 1 plus t squared, is that right? So I've got the integral from 0 to 1 of 6t square roots of 1 plus t squared dt, sorry. Just rushing a little bit, Robert. I'm Polish, not Russian. And now the integral is simple, right? It's just a u sub, right? So what's my u? Inside is 1 plus t squared, so du is 2t dt. And I have that. Right, I've got a 2t dt from the 6t. So this is 3 times t equals 0 to t equals 1 of square root of u du. I could convert my bounds if I choose to. Can anybody see what the bounds would convert to? Anybody tell me what the bounds will convert to? When t is 0, from 1 to
1 to 2.
Exactly. And now I don't have to go back to the t world. I can stay in the u world, right? I can just leave my variable as u when I evaluate. I don't have to convert back to t, which is nice. It saves a little bit of time. So this is 3 times u to the 1/2. I'm going to add 1. I'm undoing the power rule, right? And divide by my new power and evaluate it at 2 and then 1. So I've got 3 times u to the 3/2 over 3/2. So it looks like I have 2 u to the 3/2 evaluated at 2 and then 1. So 2 times 2 to the 3/2 minus 1 to the 3/2. So that's 2 to the 3/2 is square root of 8, right? And that's a good answer. I also don't mind this one. And then we can get of course we can get an approximation of this and then check it on our calculators, right?
Professor, where did the 1 plus t squared come from?
Yeah, so when I factor out the 36t, right, do you agree? 36t squared times 1 is 36t squared, and 36t squared times t squared is 36t to the 4th.
Oh, okay.
Yep.
Can you quickly go over how you determine the numbers for when you change the bounds?
Yeah, so I got my u substitution, and you see it's u is equal to something in terms of t. So I plug in the t as 0, and I get 1 plus 0 squared, that's 1, so that's where I'm starting my u at 1. And then when t is 1, 1 plus 1 squared is 2, so I'm ending when u is 2.
Oh, okay.
Yeah, it's really that simple. I mean, we had one where it was like inverse trig, and it wasn't that simple. But this one is really simple.
Can I see the bottom?
Yep. And you know, I didn't have to go into square root of 8. I could have just said square root of 2 times square root of 2 times square root of 2, right? 2 to the 3/2. So it's 1/2 plus 1/2 plus 1/2. And then I would have got the same thing, 2 red 2. But these are nice. I can do this on the calculator. I can double check myself, right? So did anyone get the same answer as me, by the way, before I waste my time showing you on this calculator? I don't want to have it wrong. And anybody get the same answer? Works.
Yeah.
Yes, thank you, Eleanor. So 4 times the square root of 2 minus 2, I get about 3.6569. And then, of course, I can go right away to that original problem right up here, right? Hoping I did everything right. Excuse me. Hoping I did everything correctly. I can just go right into that integral and see that I get the same decimal right on the test, right? Anybody want me to do it on the calculator, or is it okay if I do it on Desmos? Anybody want me to do it on the calculator? On the TI-83, 84? Charlie, is that a yes? Okay. All I need is one of you to say yes, do it on the calculator, and then I'll do that. So I'm going into my calculator here. I know it's a little bit hard to see. Don't let me lose you here. Anybody doing this along with me with your calculator? Thank you, Sarana. Angel, thank you. Iruz. Eleanor, thank you. Ash, thank you. So don't let me, Adam, thank you. Don't let me go too fast, okay? So if you are still in parametric, you got to make sure you change back. Mine goes back to function, but we were in parametric yesterday, so you might still be in parametric. Make sure you turn it back to function, okay? And I'm just going into y equal and putting in that square root that I had, right? So square root of 36x squared, oops, plus 36x to the fourth. I want to see a picture of my integral of my function from 0 to 1. So I go to my graph. And I can see the function from 0 to 1. And that's where I'm doing my arc length. How's everybody here who's going along with me on the calculator? Anybody need a second? Looks like everyone's okay and everybody's with me. So now I'm going second calculate. And I'm picking number 7, which is the integral of f of x dx. And then my lower limit is 0, I hit enter. My upper limit is 1, I hit enter. And it gives me the exact same, right? 3.6569. So it's nice to have this on the test. You can know you got something right and check it off and never think about it again. I like
How did
that.
you pick the upper limits again?
It prompts me. So when I do second calculate and pick 7, it's asking me lower limit question mark, and I just hit 0 and hit enter. Well, the limits came from the problem, Angel. I think that might be what you're asking me. But then the calculator's prompted me, what's your upper limit? 1, hit enter, and then it calculates it for me. So pretty simple. I can see myself possibly doing one with Simpson's rule. I'll do one like that today. But I want to take a look at this arc length formula if I have a function of x, right? So new page here. Oh, I forgot to get. Sorry, E. I forgot to get that thing for the dog. I'm sorry. So for parametric, right? Our arc length was the integral from a to b of the square root of dx dt squared plus dy dt squared dt. And for our explicit, or y equals f of x, I can cheat this, right? I can really think of this as x equals t and y equals f of t, right? So I can cheat this a little bit. But so what happens to dx dt? What is dx dt in this case? So dx dt is what? If x equals t, what's dx dt? So I'm taking a derivative with respect to t, right?
There's one.
It's 1, exactly. And dx equals dt, right? Right? So if you just look at that, if I have x equals t, then dx equals dt, right? The differential of x is the differential of t. And then what happens to what dy dt? What is that? What is dy dt?
So f prime of t, right?
Say again, Charlie.
F prime of t.
Yes, f prime t. What's another way of saying it? Simple. Y prime. So my arc length formula becomes
F of x?
f prime of x.
F prime of x?
F prime of x, exactly.
Okay.
Exactly. So a to b, the integral from a to b now becomes 1 plus y prime quantity squared dx. So a nice simple formula in terms of a function of x. Right, so we're going to have 2 versions of it. The book has 3 versions of it. It has the parametric. It has a function of x and a function of y. I typically don't do the function of y. I just always do it as one of these 2. Okay. So always as one of these 2. So nothing really. For us to worry about that other version of it. Let me shut my door 1 second. Good morning, puppy. Okay, let's do a problem with this version of our formula. Oh man, there's some nasty ones. This is number 14. Oh, actually, number 11. Number 11 looks challenging. Let's do that one. So this is 6.4, number 11. And I want to find the length of the curve of y equals 1/4 x squared minus 1/2 ln of x. Yuck. From 1 to 2. looks are deceiving, right? We must learn from our mistakes of basing on what it looks like to say, oh my God, I can't, don't do that. Let's see what happens. So if I got my formula down, right? So Robert's asking me for arc length. It's not a parametric, so it's got to be this version of it, right? So from 1 to 2 of the square root of 1 plus y prime squared dx, right? So all I really need is the derivative, and then plug and chug, right? I mean, it's kind of lame, which is why you can see I would put it in with Simpson's rule, right? So at least if I have one really simple problem, I can throw it in with Simpson's rule, and then have you demonstrate two things that we've learned this semester. So what do we get for y prime? It looks like what 2x over 4 minus 1/2 of 1 over x. So x over 2 minus 1 over 2x. Look right? Anyone agree with me here? I'm going to have to square it. It's a lot easier to square it if I get a common denominator. So it looks like I just need an x here and an x here, right? And then what do I get? I get x squared minus 1 all over 2x. And then I'm going to square that, right? I can kind of go into my formula now for my arc length. So from 1 to 2 of the square root of 1 plus x squared minus 1 all over 2x quantity squared. You can do your algebra on the side. You can do it inside the formula. I don't care. Right? So we're each doing our own algebra right now. You don't have to copy my algebra, right? But I know I'd get x squared minus, sorry, I'm talking to myself. No, this is an easy one, right? Again, be careful about thinking it's going to be too difficult. Just by looking at it, just start. I like to think of a math test as a free write. Like, remember when you did free writes for essays or something, and you would just start writing and see what happens. And I like to think of math problems and math tests like that. Just start writing. See what comes out, right? If you're sitting there and thinking and thinking and thinking and putting yourself in a panic, it's trouble. And this is a divide and conquer now. Not bad. Not bad. Not too difficult. Good morning, Lucy. Did you go outside? Did you say hello to doggies? Did you chase squirrels? What a life a dog has. Short but sweet. Anybody else get there yet? Anybody? Bueller? Anybody there yet? Can anyone hear me? Do I exist?
Almost.
Almost there. Okay, thank you. You'll never be a doctor if you don't have patience, right? That's what my father used to say. You'll never be a doctor if you don't have patience. Name I got there. Nice. Thank you. Charlie, yes?
I got 3/2. I don't know where I made a mistake. 3/2 plus 1 square over 2.
It could have been me. Could have been my mistake. Anybody get the same answer as mine? Anybody got the same answer as mine? Or Charlene, you get the same answer?
Yes, I got the same answer.
So Charlie, could have been your mistake, could have been our mistake. I tend to trust Charlie more than I trust myself, but we all make mistakes at times. A little mistake like having 3/2 instead of 3/4 is not going to stop you from getting an A. Right, the calculus was done a long time ago. Right, when I'm so.
I got it.
Nice, you found it. Nice.
I found it.
Yeah, oftentimes if we're working on a test, right, and then we go do this one on a calculator and it's off a little bit, and you look back at your work, it's hard to find a mistake, right? So you get a different decimal than the calculator, and then you go, oh God, I made a mistake. And then you're looking at your work, it's often very difficult to find a mistake, right? So typically what I would say to do is, one, stay calm. Let that problem go. You know you've got some good work on the page. Maybe you just made a simple error. Let it go. Do the rest of the test. Come back to it. Start it fresh, right? Unless, you certainly can look and see if you see your mistake. But most of the time we can't. When we're in something, we don't see the mistake, right? All right, let's do one with, I guess we could take a little break, maybe a little break. Well, 48 minutes. Let's do one with Simpson's rule, and then I'll derive the formula, and then I'll try it. And then we'll take a break, and then we'll decide on what we're going to do that last hour. So let's get the arc length of sine of x from 0 to pi, right? So this is my new problem, and so we're going to use Simpson's rule to do this. So find the arc length. Y equals sine of x on 0 to pi, right? So we know the picture, right? We know what sine looks like. We're looking for this length, right? We're looking for that green length. So we already know we're going to be using the equation in terms of dx, right? So we're going to do 1 plus y prime all squared, y prime squared dx, right? Square root of 1 plus y prime squared. So we already know this formula. We know our bounds. We know y, so obviously y prime is what? Derivative of sine is cos, right? And then y prime squared is cos squared. Nice.
Oh, that works out nice.
But we do have a little bit of a problem here, right? I can't really do anything with that integral. So we're going to use Simpson's rule, right? Find the length using n is 4 and Simpson's rule. So I do know at this point I'm going to start to estimate this particular thing, right? And I guess I can kind of write it down as delta x over 3. This is from memory, so please help me if I get it wrong. And then I need 1 f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3 plus 1 f of x sub 4. Right? That's the one I have. If I ask you Simpson's rule, I'm going to ask you 4 partitions. So this is the only formula you need. Will you double check it for me, please, somebody?
Yeah, that's correct.
That's correct. Okay, thank you, Charlie. So I've got a little bit of work to do here, right? I can already see my delta x. Okay, so that's nice. Delta x is pi minus 0 over 4, right? So I'm looking at pi over 4s for my x x sub i's, right? So 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, right? Etc. So it looks like I can go right into my piece now. So I'm going to get the arc length is approximately pi over 4 divided by 3. And then I'm getting square root of 1 plus cos of 0 pi over 4. Squared, right? Cos squared of that. Plus 4 times the square root of 1 plus cos squared of pi over 4. Plus 2 times square root of 1 plus cos squared of 2 pi over 4. And, and some of these will go away, which is nice. Plus 4 times square root of 1 plus cos squared of 3 pi over 4. And then 1 times 1 plus cos squared of 4 pi over 4. And I want to run this as long as I can without a calculator. I want to try and get an answer without a calculator. I want to take that as far as I can possibly go. So I'll often ask for an exact answer, an exact approximate answer, meaning don't give me a decimal, and then a decimal, right? Of course, last semester we didn't have calculators, so I couldn't ask for a decimal, right? But cos of 0 is 1. So it looks like I have here pi over 12. And I've got 1. Square root of 1 is 1. Plus 4 times square root of 1 plus rad 2 over 2. Cos of pi over 2 is 0. Cos of 3 pi over 4 is 1 over 1 plus rad 2 over 2 again. And cos of pi is negative 1, but when I square it, right? Oh, what did I do? I made a mistake, didn't I? What's the first square root of 2? Square root of 2, right? Yeah.
Yeah.
Thank you. And so why did I write 1? Because I said cos of 0 is 1. And then I wrote that instead of putting it into the formula, right? Just rushing. Just going too fast, Robert. I want to see if I can go a little bit more. It looks kind of good to me right now. I got pi over 12, and I have a 2 plus 2 rad 2's plus 8 square roots of 1 plus rad 2 over 2. And I mean, this is me. I don't know what I'm doing here with you. I don't know why I'm torturing you like this. Certainly could take out a 2. I mean, when do I stop? Hopefully soon, right? Hopefully soon.
The algebra that went on.
Yeah, so say again, Caleb.
Does the cosine squared, does it being squared have anything to do with it?
Oh, jeez. Sorry. I'm wrong. Right away, I'm wrong up to here. Sorry. Thank you. That's all right. It's time for a break. You get the idea. Right? I should have had rad 2 over 2 and then squared, right? So, yeah, that makes it a lot better, doesn't it? Pi over 12, and then I've got square root of 2 here, and then I've got 4 times 1 plus 1/2, right? Squaring rad 2 over 2, I get 2 over 4. Yes, thank you, Caleb. And at pi over 4, I still get 0. And then I get another 4 times 1 plus 1/2. Thank you. Oh boy, that's bad. Oh, it's a nicer answer now, that's for sure. Right? Not really. 2 plus 2 rad 2. I almost had it. It was 8 square roots of 1 plus 1/2. I can certainly, right, I could simplify this more. I mean, I could almost never stop. But it's enough. Right, this is what, 4 square roots of 3 halves. I'm like, Robert, please stop. That's it. I'll stop there. But anyway, let's take a break. Let's see. It is 9:58. Let's come back at in 12 minutes. 10:10. Okay.